Algebra 1 Common Core, Unit 9, Section 9, Recursive Sequences. The past two videos have been about the arithmetic and geometric sequences. Remember that the arithmetic sequences are like a linear sequence that follows a plus or a minus pattern. A geometric sequence, similar to an exponential function, follows a multiplication pattern. A recursive sequence is not limited to either one of them. A recursive sequence is another way of expressing an arithmetic sequence. So you're saying that recursive sequences can be arithmetic, they can be geometric, or they can be something else completely. So it's kind of a whole different form of sequences. And you are going to see some arithmetic sequences and geometric sequences here, but we're going to express them in a recursive manner. Basically, recursive sequences are sequences that are based on the previous term. That's what it's all about. So we tend to look at, patterns. Like if we look at this example here where it goes 3, 7, 11, 15, 19. This is a +3 pattern. A +4 pattern. So this pattern right here is a +4 pattern. And so we would say this is an arithmetic sequence, and that's true. But we can express it recursively. And basically what that means is it's just simply the previous, every number in every term in the sequence is the previous one plus 4. And so you're familiar that we use the notation a sub n to represent a term. Like a sub 1 is first term, a sub 7 is seventh term. Well, now you're going to also see a notation of a sub n minus 1. And a sub n minus 1 simply means the term before n. Because think about it, if you had numbers like if this is n, the way I get to the next term is I do n plus 1. Well, the way I get to the one before this is I minus 1 from it. So n minus 1 is right before n. It's the previous term of n. Basically, you have to train yourself that when you see a sub n minus 1, you think of the word previous. And so this sequence here can be expressed recursively as this. Now, recursive sequences actually have two pieces to it. You have to state what a sub 1 is. That's actually part of the sequence. So you say a sub 1 equals 3. So, because that's the first term right here. Then you say that a sub n, any term, equals a sub n minus 1 plus 4. And what this really means is that any term equals the previous term plus 4. Any term in this sequence is the one before it plus 4. That's what this notation means. Any term is the previous term plus 4. And you have to say that a sub 1 is 3 because just saying that it's the previous term plus 4, I can't produce this sequence unless I know what to start at. So saying that you plus 4 to get to the next one, but I can't actually create the sequence unless I know where it begins. Okay, now I know where it begins. I could do plus 4, plus 4, plus 4, and so on. Sometimes you see it in a function notation. Instead of a sub n minus 1, you see f of n minus 1. Just be aware of that. And sometimes really complicated questions, they'll try to make a sub n plus 1 the normal, and a sub n is the one before that. But let's not stress about that. That doesn't come up too often. But remember, a sub n minus 1 is previous. Let's start there. Now let's look at some examples. So we want to express the following sequences as recursive sequences. So look at A, 2, 5, 8, 11, and I could tell this is an arithmetic sequence, a linear pattern. It is a +3 pattern. So I could express it as an arithmetic sequence, and I could create my a sub n formula like we did 2 videos ago, right over here. We were, a sub n minus 1, plug it in, get a little formula. So we can do that. But that's not what they're asking us to do. That's an explicit formula. Here we're doing a recursive formula. And so the way we do it is we have to simply state that, all right, a sub 1 equals 2, because that's the first term. And then a sub n is a sub n minus 1, meaning it's the previous term plus 3. And this would be the answer. Is that this sequence, every term in the sequence is the previous one plus 3. This little notation, a sub n minus 1. And it's important that the n minus 1 is a subscript. Like, don't write it as this. That's not, it's not a n minus 1. It's not a times n minus 1. It's a subscript. It's ace and then a little subscript n minus 1. You know, like when you have y2 minus y1 in the slope formula, like y2, like it's second y. It's not y2 like that. You know, it's smaller and to the lower right side of it. So this is the answer. It's just stating the first term is this, and then the previous term plus 3 because that's the pattern. How about over here? 2, 6, 18, 54. Now this is a geometric sequence, which is basically an exponential pattern. And here I can see that it's a times 3 pattern. And so again, I could write an explicit formula like we did here in the previous video using this here, but that's explicit. We want a recursive formula, which is just simply saying, okay, the first term is 2, and the previous, and the a sub n, any term, is going to be 3 times the previous. And that's how we write that. I mean, you don't want, it's not really normal to write like a sub n, you know, times 3, like the previous times 3, like the previous plus 3. I mean, this would probably be accepted on a test, but really this is the proper way to write it. So, because remember, when you know, 3 times something, you know, it's in parentheses, and then we can do distribution with whatever that is. So this is how you would express this. The first term is 2, and you get to the next term by multiplying the previous times 3. All right, 6 times 3 is 18, times 3 is 54. All right, sometimes they give you the recursive sequence and just want you to generate the sequence. Now again, you just got to be able to look at these and say, all right, the first term is 3, and then how you would translate this is a sub n is like any term, or the next term, you could think of it as, and a sub n minus 1 is basically saying the previous plus 5. So previous plus 5, that's what this means, previous plus 5. So if my first term is 3, you know, create my sequence here. If my first term is 3, my next term is the previous 1 plus 5. Well, 3 is the previous answer, so it's a plus 5 pattern. So right here, when you see this previous plus 5, that means it's an arithmetic sequence. So plus 5 is 8, plus 5 is 13, plus 5 is 18. Done. Just one of the first 4 terms. 1, 2, 3, 4. So continue this previous plus 5 pattern until you get to 4 terms. Here, 4 times the previous, this would be a geometric concept. They're telling me the first term is 2. And what this is basically saying is 4 times the previous number. And so if my first term is 2, times 4 is 8. Times 4 is 32. So I just get rid of that little box. Times 4, well, 30 times 4 is 120, and that's going to be 128. That's it. So recursive sequences are just another way of representing these sequences. You know, like this stuff up here, we could write this as an arithmetic formula or a geometric formula, like given on your reference sheets. The a sub n equals a sub 1 plus n minus 1 times d. We could use that if we want an explicit formula. And this one we could use a sub n is a sub 1 times r to the n minus 1. These are your previous 2 videos. But a recursive representation is in this special notation using the a sub n minus 1 type of thing. But don't try not to confuse them, because it's very easy to confuse the 2 forms, recursive and explicit. You know, really, these formulas are more useful when I want a specific term. Like if it says, you know, find the 17th term or find the 200th term. Like I could jump right to the 200th term if I know the first term in the pattern. These recursive formulas, to get any term, I need the one before it. So if I want, say, the 200th term of this sequence, I need to know what was the 199th term before it, so I can times it by 4, or I can plus it by 5. So it requires you to kind of go in order consecutively, where these are, you know, explicit formulas let you jump around a little bit more. All right, but that's recursive sequences, and we will certainly practice that more. See ya.